semesterly biochemical updates on the Andrew Updates. I'm here with Caitlin Music and Claire Coogan to talk about their astounding new discoveries while working with paleomolecular biology researcher Dr. Eric Gaucher from the Georgia Institute of Technology. Their work will potentially unlock keys to providing therapy for modern-day biological medical diseases and also exposing secrets of the living conditions of ancient Earth. So, let's get right down to it. What is the point of a phylogenetic tree, and how is it useful?
Well, by tracing and analyzing ancestors of modern-day organisms, we can determine kind of what happened in the past. So typically, we use ancestral sequence reconstruction along with this. And our lab has been able to use this process to understand how and when uricase activity was diminished and to understand what the environment of the ancient Earth was like.
Okay, well, how do you test this ancient environment?
Well, the traditional way is to look at the fossil record or analyze inorganic isotopes. However, it's difficult to glean any specific biochemical detail about ancient life when essentially all biochemically relevant matter is already decomposed in the fossils and isotopes that you're looking at. So what we use in our lab is ancestral reconstruction. So rather than looking at fossils and sediment to learn about ancient life, we look at the sequences of biopolymers, typically DNA, amino acids, that belong to evolutionarily related modern organisms, sometimes distantly related. We can make inferences about ancient ancestors that these organisms had in common. We can guess what their biomolecules look like. Once we have inferred sequences, we can synthesize ancient proteins in the lab and directly test their properties.
All right, well, what specific applications do you use in your lab?
Well, one of our applications of ancestral reconstruction is using the amino acid sequence of EF2 proteins from modern bacteria with a Precambrian common ancestor to make inferences about the type of environment their ancient ancestor lived in. So, after computationally generating the ancestrally reconstructed amino acid sequences, the ancestral proteins are then made in the lab, and we test a property called GDP binding at various temperatures. So all EF2 proteins, modern and ancient, hydrolyze GTP to GDP to generate energy that they use to catalyze the reactions they perform. So from studying modern thermophiles, we know that there is a very strong correlation between the optimum temperature at which GDP binds EF2 and the optimal growth temperature of that thermophile. So the idea is that by determining the optimum temperature at which GDP binds to this ancestral EF2, we can have an idea of the environment or climate that this ancestor likely lived in. From this work, we found that the ancestor of many modern bacteria was actually a thermophile that lived at temperatures of about 60 degrees Celsius, which is much more moderate than was previously thought.
All right, well, that's all very interesting, but science is always changing and moving forward. So how does understanding ancestral reconstruction influence us today?
One big issue is that humans can no longer break down uric acid in their body, and this is an issue because if uric acid builds up, it can lead to painful medical conditions like kidney stones and gout. So this inability to break down uric acid is due to two premature stop codons in our uricase enzyme gene. And unfortunately, these stop codons can't just be replaced, and the gene cannot be just reactivated. So the FDA approved a recombinant uricase enzyme made of pig and baboon enzymes, but the issue is the half-life is too short. So they've come to the conclusion that ancient uricase enzymes are much more efficient and much more stable, giving them potential therapeutic value. And it is anticipated that these ancient enzymes will start to play an even larger role in therapeutic applications and industrial applications, and with uricase leading the way.
All right, well, that's all the time we have today on the Andrew Updates. Thank you so much for your time.